Alright, so let's identify all the carbon atoms in the structure below as primary, secondary, or tertiary. This first carbon, it's attached to 3 hydrogens and only one other carbon. It is primary. It's only attached to one other carbon. The second one is attached to 2 hydrogens and 2 carbons. So it's secondary. It's attached to 2 carbons. And this last one is attached to 3 carbons. 1, 2, 3. So this is a tertiary carbon. The edge ones, again, are just attached to 1 carbon, so both of them are primary carbons. So primary carbons are only attached to 1 other carbon. Secondary carbons are attached to 2 carbons. And tertiary carbons are attached to 3 carbons. Naming organic compounds. Organic compounds are named using the IUPAC system, the International Union of Pure and Applied Chemistry. And the IUPAC system was developed in Geneva in 1892. Basically, IUPAC is an international group where any chemist who's a member of their National Chemical Society can also join. And they meet twice a year to make sure everyone has a uniform system so that all chemists around the world are doing chemistry the same way and thus can meaningfully communicate to each other doing this. So, to name them, we find the longest continuous chain that becomes your base chain. In this case, it's 6 carbons. The longest continuous chain is 6 carbons. And then, what's coming off of it is a branch. Now, there's 2 ways we could name this compound. Starting from one end, it's 3-methyl hexane. If I count it from the other way, it would be 4-methyl hexane. You always choose to start with the carbon that gives you the lowest number. So 3-methyl hexane is a better answer than 4-methyl hexane. So we number the chain so that any branch group is on the lowest possible number. Therefore, there's only one correct way to number the chain. It has to start here because that will give you the lower number. 3 is a better number than 4. It's lower. And we use prefixes, di, tri, tetra, if there's more than one on the same molecule. And that's why we use meth, eth, prop, and bup, so it doesn't get too confusing, because we need to use both systems here. And so here we have 2,3-dimethylbutane. There's a methyl group at carbon 2, and there's a methyl group at carbon 3. 2,3-dimethylbutane. When there's several different alkyl groups, you name them in alphabetical order. And in alphabetical order, you don't use di, tri, or tetra. Those don't count. And so in this case, chloro comes before isopropyl because it's closer to the beginning of the alphabet. And isopropyl comes before methyl because I is before M in the alphabet. And so here, we name it and we count from the side that gives us the lowest numbers. If we started from this side, you'd have something on carbons 5, 6, and 7. Whereas coming from this way, you have stuff on carbons 2, 3, and 4. And so the lower numbers are correct. And again, chloro, C, then isopropyl, I, and then dimethyl, M for methyl. The di doesn't count. Prefixes don't count in this. So we got the C, I, oops, and M. So it's being done in alphabetical order. So give the IUPAC name for the following alkane. Well, let's find the longest chain. We got 1, 2, 3, 4, 5, 6. And then our branch is coming off of 2-methylhexane. If we counted from the other way, we would have gotten 1, 2, 3, 4, 5. We would have gotten 5-methylhexane, and that's not as good of an answer as 2-methylhexane. You always want the lowest number. 5-ethyl 3-methyl octane. We first draw the backbone. 1, 2, 3, 4, 5, 6, 7, 8. So our backbone is there. And it's 3-methyl, 1, 2, 3. Here's the methyl group coming off of carbon 3. And 5-ethyl. Here's the ethyl group coming off of carbon 5. The classifications of reactions will have oxidation, adding oxygen. Reduction, adding bonds to hydrogen. Substitution, exchanging one atom for another atom. Addition, two reactants joining together to form a single product. And elimination, one compound splits and forms two products. So in oxidation, when we're burning methane, we're burning natural gas to keep our houses warm. It's oxidizing and forming carbon dioxide and releasing energy. Reduction, we can reduce carbon dioxide down to methanol. And so you're gaining carbon-hydrogen bonds when you reduce. Substitution, this bromine substitutes and kicks out a hydrogen to get bromomethane. Addition, the HBr adds across this double bond. So additions across double bonds are common, and now they're all in one compound. Elimination, one compound breaks up into two compounds. We eliminate the HBr from the compound. So what is this reaction? Well, we started with one compound, and we kicked out HCl. We eliminated it, so it is an elimination reaction. Classify the following reaction. Chlorine reacts with propane, and one of these chlorines displaces a hydrogen, which was substitution. When something displaces something else, it kicks it out and takes its place. It substituted it. Combustion, again, is oxidation. Alkanes are a valuable energy source due to their ability to react with oxygen, and that's why fossil fuels are so useful. And alkanes release a large amount of energy. Alkanes are generally limited in reactivity and don't do many reactions besides combustion. So activating pure hydrocarbons is actually a big area of chemistry, because once you get a molecule like bromine or chlorine there, now you open up a lot of other chemistry. Halogenation, here's a substitution reaction. And a chlorine is kicking out a hydrogen and taking its place. This is a substitution. Dehydrogenation. If you heat a saturated alkane at a hot enough temperature, because 900 Celsius is really hot, it cracks and you start breaking it apart into multiple molecules and getting double bonds, which opens up a lot of chemistry. So this is called cracking, when an alkane undergoes decomposition to form a smaller alkane and an alkene, which is now chemically reactive. Isomerization. With enough temperature, pressure, and catalysts, we can rearrange a chemical. So isomerization is a common reaction. And here, the problem with free radical halogenation is that it's really hard to control. And so when you start this process, you get a mixture of all products when you're done. You get some methyl chloride, you get some dichloromethane, we get some chloroform, and we get some carbon tetrachloride. So free radical reactions are difficult to control, and in reality, in the end, you get a mixture of all four of these products. So reactions of alkanes. Alkyl halides are an alkane that has one halogen. And halogens are F for fluorine, Cl for chlorine, Br for bromine, and I for iodine. In general, you don't usually see fluorine and iodine very often in this stuff, because fluorine is amazingly dangerous and hard to work with, and iodine is extremely unreactive. And so your best chemistry occurs with chlorines and bromines. And then if you want to put a fluorine or iodine, you actually replace the chlorine or bromine with the fluorine or iodine. That's typically an easier way to get there. So how many dichloro substitution isomers can be written for hexane? Well, we got 12. Let's draw them out. I have hexane. 1, 2, 3, 4, 5, 6. I can have a chlorine on 1 and I can put it on 2, I can put it on 3, I can put it on 4, I can put it on 5, I can put it on 6, I can also have them both on 1. Or I could have a chlorine on 2. And we've already covered if it was on 1, but they could both be on 2, and they could be on 3, 4, 5, or 6. And then I could have a chlorine on 3, and we've already covered 1 and 3, and we've covered 2 and 3. We could have 3 and 3, three and 4, and those would be the only new ones. So if we draw them all out, all right. And it can get kind of tricky there if we put this in front of the camera. We have, they both come off of 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, 2 and 2, 2 and 3, 2 and 4, 2 and 5, and then 2 and 6 actually is not a unique isomer, because if it's coming off the end on one side and second to end on the other side, it's actually identical to this one, and so it's not a unique isomer. And then 3 and 3, and then 3 and 4, and those are the 12 different possible ways that 2 chlorines will fit on this molecule. Halogenation mechanism. We have an initiation, a propagation, and a termination.